You already know the eigenvalue equation. A times x equals lambda times x, one vector, one scalar. But watch what happens when we stack every eigenvector into a single matrix and hit them all with A at once. That single move collapses the entire eigenvalue problem into one matrix equation, and it produces a factorization that rivals LU and QR. Let's start with the atomic unit of diagonalization. A times x sub I equals lambda sub I times x sub I. This holds for every eigenpair of the matrix A. Now we define S, the eigenvector matrix. Its columns are the eigenvectors x sub 1, x sub 2, all the way through x sub n lined up side by side. This single matrix S bundles every eigenvector of A into one object. Our goal is to feed S into A and see what structure falls out. Now let's compute A times S column by column. When you multiply a matrix by another matrix, A acts on each column separately. So the first column of AS is a times x sub 1, which by our eigenvector equation equals lambda sub 1 times x sub 1. The second column is A times x sub 2, which equals lambda sub 2 times x sub 2. And this pattern continues all the way through. Putting it all together, AS is the matrix whose columns are lambda sub 1 x sub 1, lambda sub 2 x sub 2, and so on, up to lambda sub n x sub n. Each original eigenvector is simply scaled by its own eigenvalue. Here's the refactoring trick. That column matrix factors as S times a diagonal matrix. Call it capital lambda, the eigenvalue matrix, with lambda 1 through lambda n running down the diagonal and the zeros elsewhere. Why does this work? Multiplying S on the right by a diagonal matrix scales each column of S independently. Column 1 of S gets multiplied by lambda 1, column 2 by lambda 2, and so on. That is exactly what eigenvalues do. So we arrive at AS equals S lambda. This is our master equation. Let's test it on a concrete example. Take A equal to the 2 by 2 matrix with rows 2, 1, and 0, 3. Its eigenvalues are 2 and 3 with eigenvectors 1, 0, and 1, 1. So S is the matrix with columns 1, 0, and 1, 1. Multiplying AS equals the matrix with rows 2, 3, and 0, 3. And S times the diagonal matrix with entries 2 and 3 gives the same matrix with rows 2, 3, and 0, 3. They match perfectly. We have AS equals S lambda, but that's only half the story. This equation holds whenever A has eigenvectors. To isolate A itself, we need to invert S, and S is invertible only when its columns, the eigenvectors, are linearly independent, meaning no eigenvector is a combination of the others. That requirement is the critical hypothesis. We call A diagonalizable exactly when S has n linearly independent columns. Now for the two rearrangements, start with AS equals S lambda. First, multiply both sides on the left by S inverse. On the left, we get S inverse AS. On the right, S inverse times S cancels to the identity, leaving just lambda. So S inverse AS equals lambda. That is A conjugated by S becoming purely diagonal. Now go back to AS equals S lambda and multiply on the right by S inverse instead. On the left, S times S inverse cancels, leaving A. On the right, we have S lambda S inverse. So A equals S lambda S inverse. That is A rebuilt from its eigenstructure. One important caution, lambda is not the same as A. Lambda is A expressed in the eigenvector basis. The world where A acts as pure stretching along the axis. The sandwich S, lambda S inverse, translates between bases. First, S inverse converts a vector into eigenvector coordinates. Then lambda stretches along those coordinate axes. Finally, S converts the result back to the original basis. And here's another subtlety. S is not unique. If you reorder the eigenvectors or rescale them, S changes. Lambda's diagonal entries simply reorder to match the new column order. So when does this diagonalization procedure fail? It fails when A has a repeated eigenvalue that does not supply enough independent eigenvectors. In that situation, the matrix S ends up with fewer than n independent columns, S inverse does not exist, and A simply cannot be diagonalized. Here is a classic example. Take the 2 by 2 matrix with first row 2, 1, and second row 0, 2. Right? Its characteristic polynomial is lambda minus 2 squared equal to 0. So lambda equals 2 is a repeated eigenvalue. But when we solve for eigenvectors, we only get one independent vector, namely 1, 0. There are not enough eigenvectors to fill the columns of S. We call such a matrix defective, and it requires a separate treatment, which leads to what is known as the Jordan form. Here's the payoff of diagonalization. Let's compute A squared. Since A equals S lambda S inverse, A squared is S lambda S inverse times S lambda S inverse. Look at the interior. S inverse times S collapses to the identity matrix and disappears. What remains is S times lambda squared times S inverse. By induction, the same pattern holds for any power. A to the k equals S lambda to the k S inverse. And raising lambda to the k is trivial. You simply raise each diagonal entry to the kth power. For instance, take lambda equal to the diagonal matrix with entries 2 and 3. Then lambda to the 10th is the diagonal matrix with entries 2 to the 10th, which is 1024, and 3 to the 10th, which is 59,049. Compare that to actually multiplying A by itself 10 times. This is why diagonalization matters. That clean power formula drives difference equations, differential equations, and matrix exponentials anywhere A acts repeatedly. Now the family portrait. Lu from elimination solves Ax equals B. Qr from Gram-Schmidt also normalizes columns for least squares. S lambda S inverse from eigenvectors reveals dynamics, how A behaves under repeated action. 3 factorizations, 3 questions. Lu asks how to solve. Qr asks how to orthogonalize. Diagonalization asks what this matrix really does over and over.